So this section is 11.4, talking about tangent lines and derivatives. So we have 5 objectives. We're going to compute derivatives, review graphing lines, that's the little bit of section 2.2, find equations of tangent lines. Then we're going to identify the approximate slope of a function's graph. That's going to be a visual exercise. And then interpreting the derivative in the context of a word problem. I can only make 15-minute long videos with the software I use. So if I run out of time, I will make it in 2 pieces and call them A and B, and I'll give you links to both. So let's start by reviewing. That was a long time ago, last week. In section 11.3, we talked about the average rate of change and that the slope of the line between any 2 points on a graph is the average rate of change of that function. So we can analyze this graphically by looking at pictures, and we did it algebraically using algebra. So if we then take the limit as one of the points approaches the other, that limit as h went to 0 right at the end of section 11.3, we find the instantaneous rate of change at the point we are approaching. So the instantaneous rate of change is the derivative of the function. Derivatives have lots of interpretations, and this is one of them. So there's an important concept we need that's called the tangent line to a function. So if we were in class with a whiteboard, we would imagine that the blue function graph was a road and we were looking at it from above, a bird's eye view. And I would take the marker and drive it along the road, and whichever direction the marker's pointing, that's the way the tangent line goes. So if you were driving along a road, the direction your headlights are pointing, that's the direction of the tangent line. So it touches the function at one point. And if you look at this picture in the notes, you see that at P1, the red line is a tangent line, and at P3, the red line is a tangent line. But any other line that goes through that point that's not tangent to the curve is not a tangent line. So there's one and only one tangent line, and so kind of practice drawing them of, oh, it's a line that's just going to touch at one point here and kind of have the same amount of slantedness as the graph itself of the function. So the precise definition of the tangent line uses the secant line that we've been talking about, where we have 2 points on the graph, and suppose this point S gets closer and closer and closer to point R. You can see that if I keep drawing lines through those 2 points, the lines I'm drawing look closer and closer to matching up to the slope of the actual graph of the function at the point R. So the closer the point S gets to point R, the closer the secant line approaches the tangent line. So in fact, we have these 2 things that are equal. The slope of the tangent line at R is the limit of the slope of the secant line between points R and S. So if the coordinates of point R are A, so if the x-coordinate is A and the y-coordinate is f of A, and the horizontal distance between R and S is h, just like we've been talking about, where h is that small incremental distance, then we already have been talking about that the slope of the secant line would be this quantity f of A plus h minus f of A over h. So we've called this 3 different things. So let me put them all together in one place. We've called this the difference quotient. It's a difference in the numerator and a quotient. We've called it the average rate of change. And we've called it the slope of the secant line. So once we do this limit as h goes to 0, now we have three equivalent quantities. Once that limit's been applied, we have something we're going to be learning about called the derivative. Then we're going to have the instantaneous rate of change. And the slope of the tangent line. So it's a key to doing well in calculus to realize these quantities all are the same. If you get a number, if the derivative is 6, the instantaneous rate of change is 6, the slope of the tangent line is 6. But in different contexts, that 6 will have very different meanings. So let's look at an example where here we have find the slope of the tangent line to the graph at this particular point. So what we've been doing is saying let's use a because I think it's less confusing, and let's do f of a plus h. In this case it's g actually. So I'm going to have 1 minus 2 times a plus h quantity squared. So that's going to be 1 minus 2, and then we said let's don't ever do this multiplication again. Let's know that a plus h squared is a squared plus 2ah plus h squared. So then I'm going to distribute the negative 2, get 1 minus 2a squared minus 4ah minus 2h squared. So that's the g of a plus h. So that was step 1. Then step 2 was let's do g of a plus h minus g of a. That part's the difference of the difference quotient. So I copy my 1 minus 2a squared minus 4ah minus 2h squared, that's g of a plus h, minus g of a is 1 minus 2a squared. So this I'm going to get some simplifying, 1 minus 2a squared minus 4ah minus 2h squared minus 1 plus 2a squared. This is the place where everything without an h better cancel. So then the third step was to divide this quantity by h. So I'm actually going to factor out h and get negative 4a minus 2h divided by h. So that's going to leave me with negative 4a minus 2h. So this is the three things: the difference quotient, the average rate of change, and the slope of the secant line. So now when I do step 4, I'm going to do the limit as h goes to 0 of negative 4a minus 2h. Well, the h is going to 0, and making it 0 doesn't cause any problem, so that's what we do is plug it in if that works, and we get negative 4a. Well, if I asked you what the instantaneous rate of change is, now you would say it's negative 4a. Well, then the fifth thing is when x equals negative 1, then a equals negative 1. We are just using a because it's less confusing than using x. And we'll say then our answer is 4. So when x is negative 1, this is the slope of the tangent line. It's also the instantaneous rate of change, and then we're also going to learn to call it the derivative. Okay, so